Good afternoon, everybody. We're going to give everyone just a couple of more minutes to join. We'll be right back. All right, welcome everybody. Thank you for joining us today. We're having our monthly Wireside chat. Today we're going to be featuring the Taara Light Bridge. I'm Dan Lorenz. I'm Director of Vendor Relations with CTI Connect. And joining us today is Mike Puchal, who is the Director of Technical Programs, and Don Wheeler, who is the Operations Manager at Taara. As always, if you've been to these before, if you have any questions, just drop them in the Q&A. We'd appreciate any questions and any interaction that you'd like to have during the presentation. And at this point, I'm going to hand it off to you.
Hi, greetings everyone. My name is Mike Puchal. It's great to be here on this Wireside chat. I'm a Director of Technical Programs at Taara. What that means is that I engage with customers when they go through the initial phases of deploying our links. So I make sure that they have a great experience, that we answer all of their questions, make sure that everything goes smoothly when they start interacting with our technology for the first time, because as we will see during this panel, there are several differences between everything our customers usually know about RF and how our technology and how our system works. And by way of a bit more background, I joined Taara 2.5 years ago. Before joining Taara, I was the CTO and co-founder of a wireless ISP that operated in Kenya. I was based in Barcelona at the time, so working remotely, commuting back and forth to Kenya. I did that for almost 10 years. And then I joined Taara after deploying some of their links in Nairobi as a customer of Taara.
Very good. So just give everybody a little bit of background about where Taara came from, the Google Moonshot program and Project Loon and so forth, please.
Sure. So I'm gonna share my screen and go into a bit of a presentation to help us out. Okay, so as way of background around where Taara came from, Google has an innovation unit called X, formerly Google X, now known as the Moonshot Factory. This was the birthplace of several companies that you may have heard of. Waymo, self-driving cars is one. Verily Life Sciences, Loon, which was a balloon-powered internet project, and Wing, a delivery system. But there were also other projects that may not be as known, such as Google Brain, which was absorbed into Google and is now a big part of Google's AI. The thinking behind moonshots is that you take big but smart risks. You go for goals that seem out of reach, but if you achieve them, they have a really huge impact. And the goal is not necessarily to become a business success, but it's to come up with technologies that can help the world become a much, much better place. And at the same time, figuring out how the project can be a commercial success. So that's in a nutshell what X is all about. Taara was a project at X. It was born out of a combination of technology that was used by Loon. Loon used laser communications between balloons, and at the time it was deemed it was too heavy for the balloons and power hungry. And then we also borrowed some technology from Google from Google Access, which was a terrestrial link that could do high throughputs at very short ranges. So we mixed the balloon high range, low throughput with accesses low range, high throughput, and we came up with Taara's solution, which is a 20 Gbps, 20 kilometers product that consumes 40 watts per unit. And this is free space optics. So it uses light instead of radio waves. The reason for this is that this is a side view of the electromagnetic spectrum. On the left, we have 2G, 3G, 4G, 5G, so everything in the electromagnetic spectrum that we all know about. And we have been going up in frequency, trying to get more and more bandwidth through RF systems. Now we have E-band systems at 80 gigahertz. There are technologies coming up at 140 gigahertz. However, these technologies become more and more challenging as we get close to something known as the terahertz gap, which is a portion of the spectrum that's blocked by the atmosphere. You just cannot penetrate it. So we made the leap and went to the light domain, which is on the right, where we have effectively unlimited bandwidth. And we all know about fiber. That's effectively lasers going through fiber cables, and which give us huge amounts of bandwidth. So we are doing the same. We are in the early steps of the technology, but we are now able to push 20 Gbps across 20 kilometers over free space, over the air, using laser beams. So you can think about it as fiber without the fiber, with some caveats, of course, because the atmosphere still does some absorption in the optical domain. For example, clouds do have a lot of absorption in this domain. So if it is really, really cloudy, our technology can suffer the effects from that. So that's in a nutshell the introduction of where Taara came from and where it's at currently. I'll just mention briefly, we recently graduated out of Google. So one of the aims of Google X is to eventually graduate projects. And we are one of the ones that graduated. Waymo's one of the ones that graduated before us, for example. So we're on the same trajectory as Waymo. And we graduated earlier this year. So Taara is now an independent company.
So Mike, you're not a really well-known name here in the US yet, but I know that you have a lot more deployments, particularly in Africa and some in India that are, established at large. Can you talk a little bit about how long you've actually been deploying, about how many links you have out there, that sort of thing?
Yes. So there is one element about projects at X is that they focus a lot on the technology side of things. They don't focus so much on the product, on making something that's shiny and well polished, but it's more about de-risking the technologies. So starting with, is this a really hard problem that would have a really huge impact on the world? The answer is yes. So then you charge ahead and basically go through each step in the technology roadmap. And as part of that, we thought of where could we have more impact during the development of this technology, and the answer was places like India, Africa, and that's pretty much where Taara was targeting its efforts in the early days. Or Internet, one of the ISPs, one of the partners that you see on that slide, that was my ISP, my WISP in Kenya. We deployed 15 links in 2019 with Taara, and I will say that right now the focus of Taara is to become a world-class technology provider, solutions provider that where the product and the systems are well-rounded and fully built up to commercial standards, and that's where we're at now. And we are deploying in the US. We have started working with US customers for just over a year. We have many successful deployments. We have many customers and partners in the US, which means that the technology is now at a really mature stage and ready for large scale deployment with everyone from small ISPs all the way up to major telcos.
Right. Good. So it's, new, fairly new to the US, but it's a pretty well-established product already.
Yes.
So you're not the first company that's taken a crack at free space optics. There have been
Mhm.
several in the past that had their own limitations, mostly distance limitations and things like that. So Can you help us
Yes.
understand what you have brought to the table that makes your free space optics get the distance that it does and the throughput that it
Yeah.
does?
Sure. So I have been in conversations with many customers where when we say, yeah, we have a free space optic system, they sort of eyes roll and they go, oh, another one. And yeah, we've tried this 10 years ago and it was terrible. And we have several major differences with previous efforts. The first one is that previous systems didn't have an active tracking system, which means that they had a fixed optical train. So it was basically a laser pointer through a telescope and a receiver at the other end. So the alignment was critical. And because laser beams are extremely narrow, our beam is 0.002 degrees wide compared to for example, an E-band, which is a pretty narrow RF system, which is about a degree. So we are orders of magnitude more narrow than an RF beam. So keeping that aligned is extremely hard. And previous systems didn't have any form of active tracking, which means that the alignment had to be perfect. The mounting structures had to be really solid. And as a result, you could only go a few hundred feet between sender and receiver. Of course, there are systems that have been created during the years that achieve tens, hundreds of kilometers. We also hear systems reaching several hundred gigabits per second, but these are all experimental systems. They're extremely expensive. So the other key factor is that we have been able to productize this technology and using a mix of custom built components with commercial off-the-shelf components, we have been able to come up with a system that can be mass produced at a really economical price point and with a reliability that makes us able to achieve those distances and those throughputs. So active tracking, that's a major difference. A lot of technology development in terms of the modem that we have implemented into our system, which includes features that we'll talk about in a minute. So there are several differences between our system and previous attempts. I'll go into a few of these. So this is an example of the tracking system. So we have a camera built into our devices that is bore sighted with the laser beam. And in this animation, you can see at the top, this is what you would see live through the camera. We're in this video, we're in the process of pointing our link to the other side, and all of this is done through the NAP and the keyboard. So you can basically move the tracking mirror until the crosshair is on the other terminal, and then you click next, and the whole system aligns automatically, and the link comes up. So aligning this, we've just completed a training program with some partners, and we were able to bring up a 20-kilometer link in about 10 minutes using tripods. So usually the more time consuming process of bringing up one of our links is all the other infrastructure, like getting the pole brackets, getting the tower permissions, getting the fibers, run cables, power. So all of that takes a lot more time than the actual bringing up the link. So this is a key feature that our system has that previous systems didn't, which is this active tracking. Another key differentiator is that because we operate in the optical domain, we use photons to send data from one side to the other. With RF systems, you're using effectively an electrical signal. An electrical signal you can measure in terms of millivolts, microvolts. So you can adjust the modulation rate. And this is the reason why microwaves can go really long distances, but they can only give you so much throughput, up to 1 or 2 Gbps. Higher frequency systems such as E-band, they can go much faster. They can give you much faster speed, but the throughput is limited but the distance is limited by atmospheric absorption. We are in between these two, where we have the throughput and we also have the distance. And the caveat being that, of course, we are attenuated by clouds. So if you have an environment where you have a lot of cloud, we would always recommend using a hybrid system, where for example, a very, very typical use case is someone will have a microwave link, which is giving them one Gbps at say 15 kilometers. They cannot replace this with an E-band because an E-band will not go 15 kilometers. However, what they can do is deploy one of our systems in parallel. They can instantly upgrade their 1 Gbps link to 20 Gbps. And if one day there's a couple of hours where there's some clouds, they can fail over to the microwave link. So they're not going back. They go into what they had already, but most of the time they have that capacity increase. Yeah, sorry, go ahead.
I was going to say we talked about it before, how you guys do a multi-band link. If you can just share with the audience, like I know in millimeter wave and microwave, it's usually done with a layer one aggregation router, but I think you guys do it a different way.
Yes, so we do it differently. Our system is, I like to tongue-in-cheek call it a layer 1.5 device, because it's not really layer one. A true layer one device would transport whatever electrical signals come on one end and would deliver those same electrical signals on the other end. So technically you could pass anything, GPON, ATM, frame relay, whatever you wanted. Our link supports Ethernet. So anything that's Ethernet, we can pass through. However, our system implements a modem. So it's not a router, it's not a switch inside our terminals, it's just a modem, which means that whatever Ethernet comes into one port is completely transparently transported across the link and delivered out the other side without any modification. So our system doesn't support so you cannot configure VLANs or QoS or anything like that. It's whatever you deliver on one side comes out the other end. You can think of it as a fiber cable. Once the link is up, it acts exactly like a fiber. So you cannot set up VLANs on a fiber cable. So the same as us. So we're not layer one, we're not layer one, we're not layer two, we're somewhere in between. Therefore, if you want to do link aggregation, and this is one of the use cases that we will talk about in a bit, which is the Coachella deployment, we were integrated with a Ceragon microwave link and an 18 gigahertz microwave link. And the aggregation was done by a switch that effectively would keep both channels monitored, and the FSO was the primary link. And if the FSO for whatever reason came down, the switchover was immediate to the RF link. And this was done by a Nokia switch between the Ceragon and our system. And you can use any protocol. You can use RSTP, MSTP, OSPF, whatever protocol you want to use. You can use with our system. And one other key feature that our system supports is that when we detect that the link is degrading, we will proactively switch off the SFP interface, therefore overriding any timers that you may have in your OSPF configuration. So let's say that your failover takes 20 seconds between a link being detected as being degraded. We will shut down the SFP and override those 20 seconds. Therefore, the switchover is immediate. And this was evidenced at Coachella, because the people monitoring the 5G RAN that we were backhauling said that after the event, the uptime was 100%. They had no drop calls, no reestablished data sessions. The 5G RAN was effectively perfect.
Excellent. Let me remind the audience, you're welcome to post questions in the Q&A panel, and we'll take those on the fly. See you waving there, Don.
Yeah, so this is another this is an example of another feature that our system implements. We have a custom FEC and ARQ mechanism, so we can retransmit. The typical question we get from customers is, "Oh, what happens if a bird flies through the link? You know, does the link go down?" The answer is it will go down for that brief period of time when the bird is flying through, but we keep 100 milliseconds worth of line rate traffic in a buffer, and we can retransmit any of those frames that are lost during the bird flying through. And you can see this in this video. On the left side, we have error correction and ARQ off, and you can see that the video becomes choppy when that cardboard bird flies through the link. And on the right, we have FEC and ARQ turned on, and there's no interruption whatsoever. So there's no data loss. And another key difference between our system and radio is that we don't have a Fresnel zone, so we can go past obstacles that would definitely degrade an RF link, such as trees, buildings, rooftops, and so on, so we can go right past obstacles. We cannot go through them. So we recently had a case of a link that was deployed very close to the ground, and there were some trees there was a tree branch that's basically being pushed by the wind in front of the link, on and off. So we do see the link degrade when that happens. So. And then the other question we get from customers is, okay, what do you mean it goes down or up with weather? You know, how binary is it? We do have a reserve margin, so our system has a 30 dB EDFA, and typically on a 20-kilometer link with good visibility, our EDFA will only be using 7-8 dBm. So we have that power margin to overcome certain atmospheric conditions. So here at the top, you can see that with 20 kilometers visibility, this is a link, a 10-kilometer link. That remote terminal on the hilltop is 10 kilometers away. On a perfect day, everything is up 20 Gbps. On the second image, visibility has dropped to 4.3 kilometers. However, we're still able to maintain the link. So at this point, the link is still up, delivering the 20 Gbps. Even though we cannot see the mountaintop, we can still cut through that layer of cloud. And on the right, the visibility has dropped to 600 meters because there's a deep fog bank at ground level. At that point, the attenuation is in hundreds of dBs per kilometer, which means we cannot overcome that. And that's when, in a hybrid setup, we would be failing over to the RF.
So, Mike, we've got a couple of questions in the chat.
Sure.
Do you use a fast steering mirror as well as a coarse steering mirror?
Yeah, so our system, the optical train in the system uses two mirrors. There is a fast steering mirror, which is capable of moving extremely fast at kilohertz rates, but it can only move by 0.5 degrees, so plus minus 0.25 degrees. That mirror allows us to compensate for things like vibration, buffeting from the wind, tower movement of high frequency, low magnitude. And then we have a second mirror, which is the coarse pointing mirror, which moves a lot slower, but can move up to plus minus 3 degrees. So it gives us 6 degrees of range in azimuth and elevation. And those two mirrors combined is what enables us to keep track at 20 kilometers. The coarse pointing mirror is used, for example, for correcting for sunflower effect. Tower structures typically during day-night, they deform because of the heating from the sun. So that level of movement is compensated by the coarse pointing mirror because it is a slow movement, and things like vibration from wind, for example, that would be compensated by the fast steering mirror. Okay.
Another question, what happens if dirt or dust gets stuck on the lens face?
So we have the two of the links that I deployed with my ISP in Kenya are still running, and they're getting close to 6 years. Sorry, they're getting close to being 7 years up and running, and we've never had to clean the lens once. So the lens is, in technical terms, the lens is on the near field of the laser beam. So obstruction, so in any sort of dust or that kind of material depositing will not affect the link. We did have one instance where there was someone burning rubber tires below the terminal, and for some reason they had a rubber tire burning facility. We don't know why, but they just kept constantly burning tires, and eventually the burnt rubber deposited on the aperture, and just created a completely black film that eventually interrupted the link. But regular dust and dirt is not an issue. And then when it rains, it gets cleared out as well, pretty much so.
Very good. If you'd like to segue into some live deployments, that'd be great.
Sure. But by the way, I
Oh,
cannot see the questions on the chat, so you'll have to relay those to me.
yeah, we just got another one. Can you speak to deploying multiple links in a relay and the latency involved?
Sure. So the link, the latency through one of our links is 160 microseconds. Sorry, not milliseconds. So 160 microseconds round trip time, about 350 microseconds, under perfectly working conditions. When ARQ starts working because of atmospheric degradation, we start seeing slight blips in latency. So whenever we have to retransmit a frame, that frame will have an added latency. That latency can go all the way up to 100 milliseconds, and that's when you start dropping frames, because the conditions are degrading to the point where ARQ cannot keep up. So under normal conditions, if you had let's say 10 links back to back to back to back, the latency through all those links would be about 3.5 milliseconds. Of course, you would have switches between each link. Technically, you could just like plug one terminal into the other. We don't recommend doing this because you would then not be able to monitor the terminals that are placed in each tower. So you would basically go one link, drop into a switch, second link, drop into a switch, and so on. So you would have the processing delay in each of those switches, but effectively that's what you would see. So there's no added latency by just chaining links other than the latency through each of the links.
Okay, one more question just came in before we get to the deployments. Is it possible to explain how the optical axes of the built-in camera and transmitting signals are perfectly overlaid in the distance of 20 kilometers?
Yes, that's the question. The question is easily answered. The camera is bore sighted to infinity with a laser beam. So if you think about how a rifle scope works, you basically move you adjust the scope so that the bullet and the crosshairs meet wherever your target is. So we're doing the same, but we're bore sighting it all the way to infinity. So.
Very good.
Okay. All right. So I'm going to let Don. Do you want to take us through a couple of the deployments that we have on the on that slide? For example, Digicel. I think that's an interesting one.
Yeah. So, hello everybody. My name is Don Wheeler. I'm operations manager. So there's a lot of interesting deployments we've had here, specifically the Digicel one. One thing I'd like to point out is the large drum right below the gentleman who's installing the Taara link. That's one of our advantages. There is the size of our terminal compared to other RF equipment out there. Extremely small, but delivering lots and lots more data and bandwidth than those existing products. This Digicel one, I believe this was Kala Digicel. I forget the exact location, but this was a tower installation.
Oh yeah, this was Tonga. It was the island hop when they had the fiber cut.
Fiji.
Yes.
Tonga. Okay, gotcha. Yeah, I
after
don't
the earthquake.
Okay. Yeah, I don't recall some of the details on this one. My apologies.
Sorry for throwing you under the bus on that one.
That's okay. I recognize the photo, but some of the details I don't recall.
Yeah, that was after the earthquake where they had the fiber cuts on the islands. We helped Digicel recover connectivity by doing some island hops with some of our links. So that was a pretty interesting use case.
That's right.
Then Poor Internet, that photo that you see with two links in parallel. This is another key difference of our technology versus RF. We can put our terminals right next to each other and they will not interfere. The laser beam is so narrow that you can have two terminals side by side and you can aggregate both and get 40 Gbps in each direction if you really need to. And if you need even more capacity, you can put another pair of terminals, as long as you keep a 3 meter separation between the two pairs. So we actually have a test bed here in the Bay Area. We will have 4 links in parallel at 5 kilometers. I see a question.
Another question in the chat. Is there a 400-meter minimum distance? Do you have a minimum distance
Yes.
between terminals?
Yeah, so we can design, so you can design an FSO system for either really short range or very long range, but it's very hard to design a system that can go from 2 meters all the way to 20 kilometers. The reason for that is that the tracking system expects a certain beam divergence before it can start accurately tracking. If you have the terminals too close, the beam is so narrow that it creates like a hotspot in the detector that is used to keep track of where the beam is, and it doesn't have a more diffuse profile, which means that even tiny little bumps in the link in the laser beam will be overcorrected. And there's not really much you can do about that other than redesign the tracking system. So technically, we have had links that we have set up, 20 meters, 30 meters, 40 meters away from each other, but in a very, very, very controlled environment, with a few caveats and a film to also attenuate the laser beam, because at such close range, you also have a lot of power. Because again, you can choose the power to go very short distance or really long distance. But if you choose the power amplifiers that can go really long distance, then they have a minimum power level that can be that can damage some of the optics if you are too close. So that's why we have that minimum 400-meter distance. It's a combination of tracking system and laser output power.
Yeah, makes sense. Another question: are there any plans to have a product that can extend beyond 20 kilometers?
So we have done. Don, please talk about the 54-kilometer link. Go for it.
So we did close a link at 53.4 kilometers. This was a link done here in the Bay Area from Alameda up to a hilltop location called Black Mountain. And we were actually using tripods as well, well-secured tripods. But we were at a slant path going over the Bay Area, and about 70% of it was going over water. And actually, the most challenging aspect of this deployment, as I recall, was trying to find a flashing device in order to point the lasers at 54 kilometers. Our deployment process, in order for us to be able to point the laser at the very end of the deployment process, we have to know where we're pointing to. So if we've never seen our target, then it's going to be extremely difficult to point the laser when it comes time to bring up the link. So we implement the site survey process to confirm that there's no obstructions, there's no trees, there's nothing that's going to block it. And that was actually the hardest part. Once we were able to see our target, our flashing device, we used videos, zoomed in optics from some good scopes, took some still shots from both sides, and we were able to identify key features and then circle where we should be pointing. And the key advantage of one of the key advantages of our tech is we have the camera. So when it came time to bring up the link, we were able to find the features on the hilltop, point the camera directly on it, and it came up relatively quick. That was quite a challenging link, but it did prove to us the capability. Technically, I believe we are able to close a 75-kilometer link in vacuum in perfect conditions, but given a live link at this distance over the bay, and then we would have fog that would roll in over the hilltop, and clockwork every morning for 2 hours, it would drop, and then as soon as the clouds would lift, it would pop right back up to 99+% at 20 gigabits per second. So that was a proof of concept for us on what we can really do and push in the system.
Yeah, that was quite a bit. So we don't recommend doing this because, again, your availability will suffer as a result. The reason why we specify 20 kilometers as the maximum range is that That allows us to keep a reserve power margin to overcome some of those weather conditions. So if we go back to this particular slide, if this was a 54-kilometer link, and in the second image, when the visibility dropped to 4.3 kilometers, our link will go down because we would not have enough margin to overcome those clouds at 54 kilometers. We are able to overcome those clouds at 10 kilometers, 20 kilometers. And of course, if the visibility drops, the fog is thick enough, then we will go down even at shorter distances. So that's the reason why we specify 20 kilometers.
A couple more questions have come in. Since the device is using a single aperture, which exact wavelengths are used for transmitting and receiving the signal? And let me add on to that. Can you discuss the eye-safe nature of your laser?
Yes. So we use a single aperture. It's a 70 millimeter aperture, and we use a 30 dBm ETFA. That means that our device is class 1M, which means that it's completely eye safe. So you could look into the aperture of the terminal with the ETFA 30 dBm, and you would not suffer any eye damage. The only caveat, class 1M, is if you look through aided optics at a distance closer than 5 kilometers, to the link, that has a potential to give eye damage. However, you would have to be completely perfectly aligned with the beam looking through the binoculars. So the chances of that happening are close to zero. But under normal circumstances, with no aided optics, the link is completely eye safe. And then in terms of the wavelength, we use 3 wavelengths, 1 for tracking and 2 for data comms, and there's 3 wavelengths going in one direction and another 3 going in the other direction. The wavelengths are slightly shifted in towards the red and blue sides of the spectrum, and the wavelengths revolve around 1550 nanometers.
Right. Another question in the Q&A. How does this system handle wide seasonal temperature swings?
It handles them really well. We have had links deployed. Let me just see. There we have, so Poa, that's in Nairobi. You get really hot weather there. Kaust, that's in Saudi. So again, extremely high temperatures. So our system is completely thermalized. So it will remain stable through wide temperature ranges. Also in the negative.
Excellent. All right. All good stuff.
Okay, I can go into some of the deployments that we've been doing, some of the use cases. We can maybe then trigger some questions from the audience. Okay, so this is T-Mobile, one of the partners in the US that we are doing deployments with. On the left is a shot of the cell on wheels that they were using at the Albuquerque Balloon Festival. Hundreds of thousands of attendees on that one. So they had a 5G RAN deployed on cell on wheels, and they needed backhaul for it. The microwave feeder that they were using was only giving them, I believe, 1.2 Gbps. And there was again a Ceragon 18 gigahertz radio system, and we deployed one of our links in parallel, and we actually ended up running primary for the whole event with no outages whatsoever. Then on the right, we have an image of the monopalm in Indio, California, where the Coachella Festival takes place. And again, for Coachella takes place in a polo field, which usually only has a few horses grazing until 100,000 people descend onto this polo field, and the regular cell network capacity is not enough for this event. So the mobile operators do add a lot of extra capacity for the event. So there's a lot of cell on wheels. There's also a DAS that's put in place into the grounds, and all of that needs a lot of backhaul into the event. So we again provided 20 Gbps through our link, and you can see that in the middle on the monopalm. You can see the Ceragon 18 gigahertz dish and our link next to it. And the two worked in parallel. And in this particular case, India is one of the windiest places in the US. So we were seeing extremely high winds, and of course, if you're mounted on a monopalm, that creates a sail effect, and that whole tower was moving a lot. Our tracking system is designed to compensate for movement by wind, but it has its limits. If the motion exceeds that 0.25 degrees in one direction or the other direction, but in magnitude, or the speed at which the movement takes place exceeds the tracking system's capability, it will eventually cause an outage. Now, that's why we implemented this failover mechanism, this hybrid system, where if our link detected that the signal was being degraded beyond a certain packet loss rate, we would switch off the SFPs, and the data connection would automatically fail over to the Saragon RF. And we did see periods when the winds were really, really high, and that's when we had our link would start to flap. It would recover as soon as the wind died down a little bit, but as soon as the wind became high and buffety, the link would suffer another outage. And during those events, the traffic was moved over to the Saragon and then back to the optical system. And the two worked in conjunction really well. And as I mentioned, the 5G run had 100% uptime during the whole event, which lasted for 3 weeks. Another deployment that we did, this is a funny one. This is the Google campus in Mountain View. This is we call it the Dragon Scale building, and this building sits right next to Mayo West, which was the primary internet landing point for submarine cables in the west of the United States for many years. And this landing point is literally across the street from the Bayview campus. The landing point is on federal ground, so this whole complex was built, and eventually, when they had to provide fiber into this building, they realized that they had to cross several different land owners, including the federal government, and it became a really, really big project. So at the time, Google reached out and said, "Hey, can you help us out in this?" And we provided actually 2 links from 2 separate locations, each providing 20 Gbps into this campus. So that was also a very successful deployment. This is the deployment that Don mentioned. Digicel, after the earthquakes, took out a lot of submarine fibers. We were part of the restoration effort. We provided a few links to Digicel, and they used these links to go between islands to restore connectivity of the broken fiber while the fiber was being fixed. And again, worth mentioning is that you see those big drums. Those microwave links may be only providing a few hundred megabits per second of capacity, yet the load on the tower is considerable. Our systems can provide much more capacity with a much smaller footprint, and they are very quick and easy to set up. Worth mentioning, sorry, go ahead.
There's another question in the chat asking about vibration damping or stabilization mounts. Have you ever used those when you deploy? I think that's probably a little much for an earthquake region, but
yeah. So I mean, during an earthquake, if your tower is shaking a lot, the link may go down. If your tower doesn't move as a result of the earthquake, then the link will come right back up. So if your tower is shaking, you may have an outage, but then as soon as the shaking stops, the link should auto recover. Now, if your tower has physically moved, like the whole ground is shifted or the structure has shifted, our link may be thrown out of alignment. The advantage of our system is that at any time you can remotely connect to that camera view, you can realign the link, put it back to where it should be. And again, you have plus minus 3 degrees to play with. So, if your tower has moved by more than 3 degrees, your tower is possibly laying on the ground at that point. But if it has moved by, let's say, half a degree or 1 degree, you could just go into the unit, look through the camera, realign the two mirrors, run the scan, and the link would come right up. So the recovery from that event would be extremely quick. And we did have one customer that had a similar issue with a non-pen mount. They had on a rooftop, and the ballast was not enough, and the whole non-pen moved and shifted by about 0.4 degrees. So our link went down. But again, we were able to remotely access the unit, look through the camera. We saw that the system was pointing in the wrong direction, but we just realigned the mirror, and the link came right back up. So in terms of dampening mounts, because our tracking system can compensate for that vibration, we don't really need them. We've never seen the need for them. And the issue with dampening mounts is that they can induce other types of vibrations into the system. So they could actually couple other types of vibration that would be detrimental to our tracking system.
Some other related questions in here. You mentioned wind effects. The performance of your device, shouldn't the fast steering mirror be able to compensate for that? I think you've kind of addressed this already, but
Yes. So we do have various mechanisms for compensating for this. One is the tracking system itself, which uses a photo detector to measure where the laser beam is, and when it sees the beam wander off the center of that photo detector, our mirror system will automatically compensate to adjust, and this happens several thousand times per second. So this tracking system works extremely fast. Added to that, our terminals have an IMU, which include a gyroscope. So our terminals are also able to sense which way they are moving in terms of rotation in azimuth and elevation. And they are able to pre-compensate the mirror system based on that motion. So before they even get the feedback from the laser beam moving off center, they can already sense that they're moving they're being shifted in a certain direction by the wind, for example, and they're able to pre-compensate the mirror positions to adjust for that change that is going to be coming eventually. And we have seen, we actually had a 17-kilometer link in South America that was going from a mountaintop down to a building. The terminal on the building was mounted on this railing that had some 20 RF antennas, and the whole railing was shaking a lot when it was windy. And then the tower mount was also not very optimal, and was also shaking a lot. And what we saw was without this, what we call feed-forward compensation system with the gyroscopes, the link was suffering outages. Every time the wind kicked up above certain speeds, we would see the signal drop off, and then there would be an outage. When we enabled the feed-forward mechanism, the outages disappeared. The link was still moving because we saw the gyroscopes still showing that the terminal was moving just as much, but the signal was kept completely stable.
have you done any truck deployments or mobile platforms, such as for EMS or natural disasters?
Yes, we have deployed our links on tripods. We have deployed our links on cows and colts. Our links have been deployed in New York recently because of flooding has taken out fiber systems. So our links have been deployed quickly within 30 minutes. So yes, you can definitely deploy these on mobile platforms. I mean, if the platform itself is unstable, so don't put it on a boat. But if it's on like a cell on wheels or a colt that you drive to a place, you raise the mast. Yes, we have definitely done those.
Okay. Another question, is the actual beam visible to the naked eye at night? I think you operate at higher frequencies than visible light, right?
That is correct. We operate at 1550, which is infrared, so it's not visible. That's also a key aspect of our technology. Our system is extremely secure. It cannot be detected. It cannot be intercepted. So we have a lot of interest for defense and high security applications, where even fiber can be tapped. Our system cannot be intercepted, cannot be monitored. So it's completely indetectable, therefore extremely secure.
One more question here. Do you have any plans for higher data communication rates by implementing coherent communication?
Yeah, so coherent would be very hard to do at a low price point. The development cost for working coherent through free space is pretty expensive. So not by the use of coherent. We could technically go up in higher in data rate. Our system has enough bandwidth to go higher. What we have seen is that there's no demand so far for FSO systems at much higher rates, other than let's say more edge use cases where we have a customer that says, look, I have two data centers and I need 400 gig between the two data centers, and my fiber doesn't come in, it's going to take a year to build between the two sites because of right of way permits or such issues. So we've had a few customers asking for higher data rates, but let's just say that the market is still in the early stages of adopting this technology. And the cases where we see the need for much higher data rates are still a few far in between.
Good. I think that's all the questions that we have open at the moment. We're at 1:50 Eastern, so about 10 more minutes left on the clock. If there's any other last minute questions that you guys want to get in. What is this
I will
deployment here,
also.
Mike?
Yeah, so this deployment is a tribal community that had connectivity issues, and they couldn't run fiber. They were pretty much in the middle of nowhere. So again, we helped them provide 20 Gbps of throughput to effectively they were running a WISP on the back of this. So we helped them deploy our links and get much higher throughput to the members of the community. I will say that our systems can also be used for BEAD rollouts. And of course, because you don't need any licensing or any right-of-way permits, there's no frequency coordination. You can just order them and deploy them. You don't need to ask anybody for permissions, and you can also go through airports. So we have FAA clearance. So if you have an airport in the way, you can also go through an airport if you have to. So our system is very versatile in that respect. So
That's interesting. I didn't know that one. That was a good tidbit right there.
yeah, and the other use case that we have customers deploying Taara, and Taara of course can deliver pretty high throughputs. And what we've seen customers ask is that, well, they deploy a Taara tower, and when they're fully loaded, they don't have anything that can provide enough backhaul to those towers. Especially once they start, especially if they have a hub and spoke type topology, they get to the point where the towers around the edges don't have enough backhaul capacity to be fed. So we do see some of these newer RF multi-point distribution systems that have pretty high throughputs. They need more backhaul capacity than what RF can provide.
Yeah, we've heard that a lot from our customers. They're, as you said, and the Toronto G2 is now, consuming twice the bandwidth. So you get four of those things up on a tower, and it's
Right.
it's a real beefy system, right? And you have to have a really heavy
Yes.
backhaul to get out there.
Yes.
I think a lot of people have
Yeah.
considered using your product too, where they're supposed to have a fiber fed tower, but the tower's not fiber fed yet. And
Yes.
it allows them to deploy today while they're waiting on fiber to be trenched tomorrow,
Yes.
And
Yeah.
certainly if there's right of ways, or if there's a waterway in the way or whatever, if you just can't trench fiber, it's a good way
Yes.
to bridge the gap.
Yeah, so we have had WISPs that they may be offering, let's say, a 20 Mbps product through regular unlicensed 5 gigahertz systems, and they're upgrading all their infrastructure. And they have places where they've already upgraded the infrastructure, and they're offering 100 meg plans, 500 meg plans. But as you say, those depend on fiber being available to provide the backhaul. What we've found is that with our system, they can start providing those higher throughput services faster while they wait for the fiber to arrive. So they can start promoting and offering those higher highest rate services sooner than they would otherwise.
We have another question asking if you're going to move into
Yep.
space deployments. I don't know that that's a topic for most of this audience, but any plans to do that?
Yes.
Ground
So,
satellite?
so our terminals, interestingly, will survive re-entry, which is something that we're very proud of. However, for a space system, that's bad. Any space system needs to have something called demisability, which means that if you deorbit a satellite, all the components need to burn up upon re-entry, so you don't have any pieces of the satellite hitting the ground. Joking aside, we're not right now. We don't have anything in the roadmap specifically for space applications. Whether we do or not, that depends on finding the right partner. I know there's a lot of interest right now in satellite, so satellite to satellite and also satellite to ground. There's companies already building products for these markets. However, we are currently focused on terrestrial applications.
Yeah, I would expect that. Well, we're 5 minutes from the top of the hour, so we'll give everybody one more minute if there's a remaining question to be asked. Please get it in here now. Any final remarks you'd like to make, Mike or Don?
Don, you want to go for it?
Yeah, this image that you have up here, this slide is one that I had actually pulled up on the side, and there's been some other deployments in Africa that this image has a lot in common with. But I just like to point out some of the size differences, the ease of deploying. There's one image that I had. There's a tower in Africa that's similar to this. It shows all these massive drums and all this equipment. There's probably 30, 40, 50 RF links. And I really like to look at that little tiny dot, and it shows where our little terminal is. That actually delivers more throughput than the entire tower combined. So this is just one of the things I really like about our technology, and also a lot of feedback from the riggers and the installers who have to carry ours up. They really prefer that little dot over that big 10-foot drum when it comes to the installation. So the ease of installation is a really key part of our technology, and I really like hearing the good positive feedback from the experiences from customers and installers on how easy it is to install.
Yeah, and that really speaks to the total cost of ownership, because you're renting less tower space, you're using less power, and once you factor that into the equation, it becomes a lot more attractive when you've got such a small footprint on the tower.
Correct.
Let's see. Does CT? So there's a question. Do we make fiber power cable management like pictured? Yes, the answer is yes. We have manufacturers that are doing hybrid cables and so forth, and we can have those custom made to length. All right,
And the
gentlemen.
question about
Why don't we? Oh, one last one. What is the power draw? It's 40
power draw
watts,
is
correct?
40 watts. Yes, that is correct. And I can also quickly answer the one about wavefront errors. We use on-off keying, so we don't need to correct for wavefront errors.
40
Yes.
watts at
Yes.
48 VDC.
Yes, that is correct.
Yep. So I think we've hit everything. We're at the top of the hour. Oh, but any variation with PoE versus DC?
No, so you can run both PoE++ and DC at the same time. There's no variation. The terminal will draw whatever is available. And on the wavefront, there is no coupling. We have a whole set of filters and an optical train that takes care of that, but we don't need polarity maintaining fiber. We're polarity agnostic, so you can actually we've had customers that deploy the links on the tower at an angle or on an angle leg and the other side at another angle, and there's no issues. We don't care about the polarization like you do in RF. Negative 48, yes, it's polarity agnostic. You can do plus minus 48 volts. It doesn't matter. You can connect them either way. So if you're on a cell tower that runs negative 48, you can power a system from it. I like how everybody's trying to get all the questions in there.
Yeah.
Well,
once
if
you
there's
get
any
the
other
gears
questions,
turning,
yeah.
once you get the gears turning in these things, then that's when the questions start flowing. So yeah. All right, folks. I think we're about ready to wrap. Gentlemen, thanks so much for the presentation. We really appreciate it. Audience, if there's any further questions that you have, or if you'd like to discuss any applications that you have for the product, please reach out to your CTI Connect salesperson. All right. Thanks, everybody. Have a great weekend.
Thank you so much.
Thank you.